This is Radio Eco-Shock with Alex Smith.
Just back from the American Academy for the Advancement of Science Annual Conference 2012, this is Alex Smith. I've recorded two of the best speeches of the weekend gathering of thousands of scientists held this year in Vancouver, Canada. Dr. James Hansen, head of the NASA Goddard Institute for Space Studies, warns it isn't enough to reduce our emissions. We must actually take carbon dioxide back out of the air to avoid entering a new and dangerous age of greenhouse living. We are currently at 390 parts per million CO2 in the atmosphere and rising rapidly. The target, Hansen says, is 350 parts per million. That is the level where the polar ice, which regulates the climate, humans have known for the past 10,000 years, will remain on planet Earth. Both are short recordings from the AAAS symposium titled Climate Solutions, The Challenges of Getting to 350. They were recorded by Alex Smith on Sunday, February 19, 2012. Here is famed climate scientist Dr. James Hansen.
Let me go right to my first chart. So this is the global temperature the past century, and there's now no disagreement that the world has warmed up about 0.8 of a degree Celsius over this time period. Even the skeptical scientists now agree with that. And that's putting us already beginning to move outside the range of the Holocene. Civilization developed during the Holocene, the last 10 to 12,000 years of relatively stable climate. These are curves for the temperatures estimated at different places on the Earth's surface, multiplied by factors to make the curves approximate the global mean temperature change. So the polar regions, for example, the top of the Antarctic ice sheet, the temperature changes are typically twice as large as on the global average. So they're multiplied by 0.5. But you can see that over the last 8 or 10,000 years, the temperature's been relatively constant. And we can say with a pretty high degree of confidence that we've already moved out of the Holocene range, because these are graphs of the mass balance of the Antarctic and Greenland ice sheets, and measured very precisely by the gravity satellite GRACE. And what it shows is that both hemispheres, the ice sheets, are now losing mass, and the rate at which they're losing mass is accelerating over the period of the data, which began to be measured in the late 2002. They're now losing mass at a rate of a few hundred cubic kilometers per year. And sea level is going up at a rate of more than 3 millimeters a year, which is more than 3 meters per millennium. And if we compare this to the Holocene, sea level has been very stable within about a meter or so over the entire past several thousand years. So we're now already at a point where it must be a bit warmer than the prior Holocene maximum. This is the temperature over the past 5 million years on the top graph, and then it's expanded over the last 800,000 years in the bottom graph. And the 0 point on the temperature scale is the 1880 to 1920 mean, with the assumption the modern temperature record is attached to this temperature record, which is extracted from microscopic shelled animals that lived in the deep ocean and deposited their shells on the ocean floor. But from those, we can get an estimate of the temperature variation over this time period. And you see that now that the temperature is at about 0.8 of a degree Celsius, it's not quite as warm as the last interglacial, which was probably about, according to this record, about 1.2 degrees Celsius. So we're still about half a degree cooler than the last interglacial period. But we're only about 1 degree cooler than the early to mid-Pliocene, when sea level was 15 to 25 meters higher. So if that gives you an idea of the limitation. Even if we go to 2 degrees Celsius warming relative to 1880 to 1920, we will be pushing the climate toward eventual sea levels of tens of meters higher than what it is now. We can't say how long it would take to come to that new equilibrium if we brought the planet to 2 degrees warmer, but we know where it would be headed. And in my opinion, we could expect multi-meter sea level rise this century. That's one of the criterias for helping us estimate what is the level of greenhouse gases that we should aim for. Another one is another irreversible effect, practically irreversible on any time scale that humans can imagine, is the extermination of species. And we're already putting a lot of pressure on many species. And if we go with business as usual for the rest of this century, the estimates are that 20 to 50% of the species on the planet would be ticketed for extinction. But it's not only these long-term effects that we need to be concerned about. The climate already is changing. This graph on the left is the frequency of occurrence of summer mean, June, July, August temperature anomalies relative to the 1951 to 1980 mean climate. And that's an appropriate base period to use because that's still within the Holocene, which is the period to which the biology on the planet is adapted, life on the planet is adapted. And we can see that we have the curves for this frequency distribution for different decades. The 1950s, 1960s, 1970s, those 3 decades all have the bell curve, the normal distribution for the distribution of anomalies. But now you see in the last few decades that distribution has been shifting to the right. And not only is it shifting, but it's getting broader. So you can see that there now is a significant chance of having a 3 standard deviation anomaly, which, if you go back to the period of climatology, a 3 sigma deviation occurred about 2 to 3/10 of 1% of the time. Well, it's now more like 10% of the time. These are maps of the anomalies in units of standard deviation. So the 3 sigma anomalies are the dark brown. And if you look in the 1950s, 60s, and 70s, they hardly occurred at all. But now in the last few years, they've been occurring over about 10% of the land area. So in 2011, Texas and Oklahoma and northern Mexico had a 3 sigma anomaly. And the prior year, 2010, Eastern Europe and Western Asia had an anomaly, a 3 standard deviation anomaly. That was what was hitting Moscow a year ago. So those anomalies are now, you can say with a high degree of confidence that in fact those extreme conditions in Texas and Oklahoma and Moscow are attributable to the global warming because their chances of occurring were minuscule prior to that warming. And that's an indication of what's to come if we stay on business as usual. This happens to be computer simulations of the likelihood of extreme summer droughts from the ECMWF climate model. But it just shows these regions in southern Europe and Mexico and the Midwest of the United States. There's a danger that breadbasket of the country, or breadbasket of the world really, will be plagued by extreme droughts if we stay on a business as usual course. Now, there are a number, in longer presentations, I can give you a lot of reasons why it makes sense that the maximum level of CO2 that we should aim for on the long run is no more than 350 ppm. But we can quantify that quite precisely by looking at the planet's energy imbalance. This shows, this is a graph of the solar irradiance over the last few decades, the period in which it's been accurately measured from satellites. And what we'd like to know is the planet's energy balance or imbalance. And finally, with the deployment of the Argo floats, of more than 3,000 floats around the world's ocean, which measure the temperature and thus the heat content of the ocean to a depth of 2 kilometers, we finally have a reasonably accurate estimate of the rate at which the heat content of the ocean is changing. And what we find over this period in which we have the most accurate data, the last 6 years, is that during that period the ocean is gaining heat at a rate of about 0.4 of a watt per meter squared averaged over the planet. And when you add in the amount of energy that's going into melting of ice, the reduction in the size of the Greenland and Antarctic ice sheets and the mountain glaciers, and the heat going into the atmosphere and the ground, it's about an imbalance of about 0.6 of a watt per meter squared. And that's occurring during the solar minimum. So if the sun were driving the system, then during the solar minimum you should have less energy coming in than you have going out. But in fact, there's more energy coming in because of the greenhouse effect of the added gases. And the imbalance is about 0.6 of a watt. So averaged over the solar cycle, the imbalance is probably more like 0.75 of a watt. For if the imbalance is 0.5 a watt and you wanted to restore the planet's energy balance, keeping other things fixed, you would have to reduce CO2 from 391 ppm to about 360 ppm. If the imbalance is 0.75 of a watt, you have to reduce CO2 to 345 ppm. So that's very consistent with our estimate that we had made a few years ago, that you need to get back to about 350 ppm. You know, if we put a pulse of CO2 in the atmosphere by burning fossil fuels or otherwise, the atmospheric amount will decline over time as that CO2 gets mixed among the surface reservoirs, especially going into the ocean. And after 100 years, only about 18% of that pulse is still in the atmosphere. But most of that will stay in the atmosphere for millennia until it's finally deposited on the ocean floor as carbonates by the weathering process. But it's important to note that the same thing is true for a negative CO2. If you decide we've passed the safe amount of CO2 and so we're going to suck some out of the atmosphere by whatever means and then store it, if you suck out 100 ppm, well, the effectiveness of that will decline over time because the ocean will then feel, oh, there's less CO2 in the atmosphere, so it will start degassing CO2. So the same curve applies to a negative. So if you want to suck the CO2 out, you've got and have it stay that change remain for 100 years, you've got to take out about 6 times more than the decrement that you want to get. So geoengineering in that way is going to be extremely difficult. And in fact, with today's costs, if you had to take 50 ppm out of the atmosphere, the cost would be a few $100 trillion at the current with current technologies for trying to get CO2 out of the atmosphere. You may be able to reduce that by a factor of a few, conceivably even an order of magnitude, but then you're still talking about tens of trillions of dollars just to get 50 ppm out of the atmosphere, and then figure out what you're going to do with it. On the other hand, it's not impossible to get back to 350 ppm. If we stopped emitting CO2, if we stopped burning fossil fuels in 2015, we would go back to 350 ppm about the end of the century. If we waited until 2050, it would still be over 400 ppm for several centuries. But if we also assume that we could reforest and we could store in forests and the soil 100 gigatons of carbon, that would be essentially, that's about the total amount of deforestation that has occurred over the last few centuries. So it would have to restore forests to comparable to what they were earlier. But I think that's barely conceivable, because you could also get some of the